and I'm here in heat pumps laboratory in KEZO Research Center, which is a part of Instytutu of Fluid Flow Machinery of Polish Academy of Sciences. Here in this laboratory we have a few different heat pumps that are used to cool and heat our building. If you don't know what a heat pump is, I'll briefly tell you. The heat pump is a device that uses low temperature source such as ground sources, water sources, or outside air sources to deliver higher temperature energy that can be used to heat a building or heat hot water, domestic hot water. They take external energy source such as electric grid or gas. They're very efficient because the heat delivered, this heat that we use to heat a building, it's often up to 5 times larger than the heat that the energy supplied from external source. As I tell you, from the grid or from the gas sources. Now let me show you what kind of heat pumps we have here and how are they made. Here we have a small heat pump that is mostly common. It can be used to heat common households. Let me show you how it's made. Every heat pump consists of 4 main elements. The first element is a compressor. Compressor is used to compress the gases such that the temperature of the gases rises, of course, as well as the pressure. With the high temperature, we can take this energy in condenser. We use the gases to transfer from one side and the heating system water from the other side. The temperature of the water rises and we can use this heat to heat our building. The temperature of the gas inside the heat pump falls down and it condenses to the liquid. Such liquid is then transferred to the expansion valve right here. What it does is lower a pressure by expanding. When it expands, the temperature suddenly drops to very low value, such low that we can use external source such as air to evaporate it in evaporator. I will show you the evaporator of this heat pump in a second because it is placed outside of the building. When the liquid is evaporated in an external evaporator, it goes back to the compressor when the cycle closes. Guys, this is the evaporator of this heat pump that I show you just in a second. What it does, the low temperature liquid is delivered here and it goes all the way across, up and down in this radiator. The liquid is much colder than the air outside, so such as the heat from the air is transferred to the liquid and it evaporates to the gas. And it goes right back to the main building, to the compressor, such as I told you before. Here we've got a very big heat pump that is different from the commonly used ones because this is high temperature source heat pump. Why high temperature? Because it can deliver up to 90 degrees Celsius of heat source. So it can be used to such as domestic hot water system or the building heating, which has radiators instead of floor heating that needs a higher temperature source. It's somewhat different from the commonly used one because it works in a transcritical cycle where the refrigerant used is CO2. Let me show you what's different from the commonly used heat pumps. Here you can see a compressor. What's different about it from the others is that CO2 refrigerant works at a much higher pressure, such that the compressor needs to be a little bit different, so it can work in higher pressures and can deliver up to 14 megapascals of pressure. Nextly, we don't have a condenser because the CO2 in the cycle is compressed to such temperatures and pressures that it goes into transcritical state. In transcritical state, we don't condense the CO2, we just cool it, and we do it in a gas cooler. This is a gas cooler, and it's in a place in normal heat pumps where is a condenser. It cools the transcritical CO2 such it goes into liquid. When it's a liquid, we have two expansion valves. Those are normal, like in a commonly used heat pumps. And then the liquid CO2 goes to the evaporator when it's cooling the water, the lower source, and it evaporates and goes back to the compressor. Here you can see the lower and upper source. The lower source is here in this black isolation. We use this black isolation to prevent condensating water from the air. Because the pipes are much colder than the air, there could be condensation from the air. As you can see, we need a big pump to deliver this water that goes through the evaporator and cools down. Here lower you can see the upper source pipes. The pump is over there behind the wall. You cannot see it now. As you can see, it goes right into the gas cooler when it takes energy from the cooling the CO2. As you can see, we have temperature measurements on every pipe, and as well we have a flow measurement over there. And right here. We use these measurements to calculate the heat delivered and heat taken, as well as the measurements of electricity used to power the compressor. With these measurements and calculations, we know characteristics of this heat pump, and we can calculate the COP or EEF. As Veronica told you, or maybe will tell you, we use this BMS, which is Building Management System, to control every device here in KEZO. As you can see, this is the Mayakowa heat pump that I showed you right before, and now I want to start it. So the first thing I need to do is to power the the pumps that pushes the lower source here and the upper source water here. As you can see, we have the measurement right away, and we can see what's going on right now. And now we will proceed to power on the heat pump itself. As you can see, the heat pump is starting right now, and you can observe the temperatures and pressure on the screen. Take a closer look at the pressures. The first pressure, PE01, is the pressure after the compressor. So the pressure of the gas that is exiting the compressor. You can see it goes, right now it's 11.6 megapascals. And the temperature of it is the TE.1, the 001. The first temperature on the right. Right now it's coming up to 90 degrees Celsius. The next pressure that you can see, the PE02, is the pressure at the section of the compressor, before the compressor. So the liquid, the gas CO2 enters the compressor at the pressure 4 megapascal right now. And the temperature of it is 12.4. This is the temperature 02, PE02. The next set of temperatures are TE.3 and TE.04. These are the temperatures of the upper source. So the water of the upper source comes right in of the temperature 27.7 degrees Celsius, and it's heated up to 59.6 right now. And we use this water, this high temperature water, to heat up our building. The next temperatures, TE05 and TE06, are the temperatures of the lower source. So the water of the lower source comes in at 12.4 degrees Celsius, and it goes out at 8.5 degrees Celsius. With this water, we can use it to cool the building in our building cooling system, or we can take energy from the environment to heat it up. We have a couple of different ways of doing that, such as ground source and air source and water source, as I told you before. As you already know, the evaporated CO2 in the evaporator goes right back to the compressor. To prevent event in which not all CO2 is evaporated, so such as some of the CO2 stays in liquid form, cannot happen because the compressor will be destroyed when the liquid gets into it and it gets compressed. We need to supply some overheating, or what is called superheating. You can see it's at the lower part, which is SHC1 and SHC2. This is a temperature reading of how much degrees Celsius the CO2 is overheated or superheated up to the gas state. Why we have two? Because as I showed you before, we have two evaporators. So we measure two different temperatures, and we control the expansion valve in a such way that we have enough superheating that we make sure no liquid gets into the compressor. As of right now, we are operating at the temperature of the lower source return at 37.8 Celsius. We can see the parameters right now. Take a closer look, and now I will begin to lower the upper source return temperature, so TE04. I will begin to lower it down, and I want you to take a closer look at the other parameters of the system and how they change according to the change of the upper source return temperature. We will take a closer look at the CO2 diagram later, and we will compare two different cycles at two different temperatures. I'll begin to lower the temperature right now. We can see it falling down right now, and let's see the response of the other parameters to this change. You can clearly see the pressure PE01 rapidly falling down. That's the obvious change, and we will see it on the diagram as well later on. The upper temperature return should stabilize at around 20 degrees Celsius, and that's the point. We will take the measurements and put it on the diagram later on. You already know that we utilize produced heat to space heating or domestic hot water heating, but what do we do with produced coolness? When there is a summer and we want to cool the building, we store the cold water in such as tanks. This water we can then supply to the fan coils using this pump, or to the ventilation system to cool the incoming air to the building. But in the winter we will need to take energy from the environment, and I will show you how we do it. Right now we are outside of the KEZO center, when I will show you the borehole storage system. This system is used to take energy from the ground using U-pipes. They go all the way inside 80 meters low into the ground, and the fluid inside transfers heat from the ground to itself, heating up. Then we use this heated up fluid as a lower source of the heat pumps. We have 53 of these vertical U-tubes to take energy from the ground. Here we have a pressure enthalpy diagram, commonly referred as pH diagram. It is used to show the refrigerant cycle in heat pumps and refrigerators. Here it is R744. which is pure CO2, exactly what we have in Mayakowa heat pump. On the diagram you can see 3 cycles that I drawn to represent different parameters, different cycles at different parameters. The energy from the lower source can be calculated as a mass flow times the enthalpy difference. The enthalpy difference here is the energy taken from the lower source. The enthalpy difference here is the energy supplied by the compressor, and the enthalpy difference here is the energy supplied to the upper source. So here you can calculate how efficient is a heat pump at different cycles. If we use the supplied heat and we divide it by supplied energy in the compressor, we can calculate the COP for the heating, and if we take the heat taken from the lower source, we can calculate the COP for refrigerator. So the main point here is to demonstrate efficiency at different temperature levels. Here, this point represents the point at which CO2 enters the expansion valve. It expands here, lowering its pressure to a lower level when it gets to the evaporator and evaporates. This point depends on the upper source return temperature. This is the parameter that we change during experiment. Here, this point is on the 45 degrees. That could be represented by the measurement we took of a upper return temperature of 38 degrees, because we have some temperature difference in gas cooler. Then we have this blue cycle where the temperature is much lower. Right here is around 13 degrees. We can see when we lower the upper temperature return, upper source temperature return, we get much higher energy delivered to the upper source, as well as much higher energy delivered in the lower source, where the energy delivered to the compressor stays roughly the same. That means this blue cycle is much more efficient than this red cycle. As you already know, to make a characteristic of a heat pump, we need to take several measurements at a different temperatures level, such as we did with the Mayakowa heat pump at the different temperatures, upper source temperatures return. But to be precise and do this correctly, we need to maintain a set temperature for a period of time. To help us get this temperature right and stable at the set level, we use another heat pump as well to stabilize this temperature. This is a workstation to take a characteristics of heat pumps. What it does is to stabilize the upper source and lower source of temperature of the water that is supplied to the heat pump. Also, also, it already takes measurements of these temperatures as well as the heat flow, as well as the mass flow, that we can calculate the heat flow. Using that, we can save this data using the computer and get this characteristic right.
Hey guys, my name is Krzysztof, and today I'm going to tell you about photovoltaics. As you probably know, number of photovoltaic system is growing rapidly all around the world, also in Poland. Usually when something happens in rush, a risk of failure grows too. That's why testing of photovoltaic modules is an important issue. It provides reliability of photovoltaic systems. Usually, you can perform a few tests to check how your device performs. One of the most popular tests, which is performed in every photovoltaic module factory all around the world, is taking an IV curve of photovoltaic module. What is the IV curve? This is current voltage characteristic of photovoltaic module. To get it, you have to you have to have a few important things. So that's why we are in a laboratory of solar techniques in the KEZO Research Center. Here we have many devices which are utilized to perform measurements of photovoltaic modules, but also solar collectors. The main device in this room is a sun simulator manufactured by Eternal Sun. This simulator is the large area steady-state sun simulator of AAA class. What does it mean, AAA class? Okay, so every A is let's say every A express the feature of this simulator, namely stability, spectral content, and uniformity of the light which it provides. This very high class make us sure that our measurements are really precise. Of course, you can use different sources of light, but then the uncertainty of your measurements grows. So we have this very well sophisticated sun simulator, which allows us to perform measurements according to international standards like IEC 61215. This is one of the most popular standards, which determines how to check if your module simply work in proper way. So, how to perform a single measurement of photovoltaic module? Here we have a photovoltaic module which lays on a, let's say, kind of table. It's important to provide complementarity of photovoltaic module and reference cell. What is reference cell? Reference cell is a specially calibrated piece of photovoltaic cell which is used to measure the irradiance. So let me check if the complementarity occurs. It's maybe you can see not exactly. So let me fix it. Okay. So here we go. Now we can check if okay. Yep. Okay, now I think it's better than it was. So this is the first thing. Second thing, we need to control temperature of device. Why, I will tell you later. This is a PT100, some kind of resistant sensor. So I take a piece of tape and glue the sensor to the rear side of the module, more or less in the middle of the device. Okay, so we've got it. Next thing, to take the IV curve, we need to measure, I think it's obvious, current and voltage. So I use these two connectors, and also I'm taking terminals of photovoltaic module. Oh, that's not easy. To connect this module to the tracer, which is behind. Okay, so now our model is almost ready to measure this. But firstly, few things which are important. According to the standard, we need to perform our measurements in standard test conditions. It means that the temperature of our model during the measurement has to be equal 25 degrees of Celsius. Second thing is that irradiance needs to be 1000 watts per meter square. And the last thing is that optical mass needs to be equal 1.5. Optical mass is a term connected with, let's say, spectral content of light, and this simulator provides us this required optical mass. Okay, so here we go. We have our sensors, we have our model ready, and also we know what are the conditions in which we should perform the measurement. One important thing is that to provide the uniformity of temperature of the model, we firstly need to cool it down, because when we move the table and put the model under the sun simulator, its temperature starts to grows rapidly. So the temperature of the model before the measurement needs to be, for instance, let's say 3, 4, maybe 5 degrees of Celsius lower than 25 degrees. Yeah. So let's put the model under the sun simulator. So during the normal measurements, it looks like that. Because we have some, well, problem with sun simulator currently, I cannot switch it on. So just imagine it just shines. Okay. Let me show you the after mentioned tracer. This is a setup which consists of a few things. Of course, PC with some specialized software. Second thing, 3 multimeters which measure current, voltage of photovoltaic module, and also first one which measure the voltage of reference cell and recalculated to the irradiance. Okay, also we have electronic load. This electronic load is used to change the resistance of and that's why we can measure the voltage and current in different points, and as a result we get the characteristics like that. This is a typical characteristic of photovoltaic model. As you can see, we have, of course, 2 axes. One is voltage, second one is current. Typical characteristic is similar to the characteristic of diode. Okay, there are a few, let's say typical points of characteristic which we want to know to determine if how module performs. First one is short circuit current, which is here, and it's a current which we get when the circuit is shorted, according to the name, and when the voltage is equal to 0. Second point is open circuit voltage, and as follows: the current is equal to 0, and our voltage is then let's say gray. And next point is maximum power point, and for this point we have current and voltage, which provides that their multiplication gives us the biggest power. As we can see here, because we have the second curve here, this gray line, and we can see that the optimum is here. Thanks to these 4 points, we can calculate fill factor. Fill factor is a value which gives us information how good is our model. How to calculate it? So you need to divide the area of this square, which is described by maximum power current and maximum power voltage, and you need to divide it by the area of the square of rectangle, to be more precise, of rectangle, which is determined by the short circuit current and open circuit voltage. So this is the one parameter. You want to get as high as possible fill factor, and if your fill factor is better than 75%, it's good, but really good it's about 80%. What's more? Also, you can calculate efficiency. Efficiency is maximum power divided by the area of the module times the irradiance. As I said, the irradiance should be equal to 1000 watts per meter. But, well, in reality it's almost impossible to have this value because there are some small fluctuations of irradiance under the sun simulator. Also, the temperature is usually equal to 25 degrees, but not also. So there are some formulas according to the standards which enable to correct obtained values to the STC values. Of course, you cannot use these formulas always. There is a range of temperature and range of the irradiance in which they are valid. Among different methods of testing photovoltaic models, one of most commonly utilized technique is electroluminescence test. Luminescence is a feature of some materials which, well, when you provide some kind of external impulse, some material starts to shine, let's say. In case of electroluminescence, this external impulse is simply current. And this feature is also occurs in case of photovoltaic models. Thanks to this phenomena, you can detect if some parts of your photovoltaic model are damaged or some impurities maybe occur, etc. So, in case of silicon cells, the most popular ones, when you provide the external source of current, they start to shine in a near infrared. So you cannot see it with the naked eye. That's why a special device is required. Also, because this shining is very weak, the test should be performed in the dark room or during the night to make it possible to see this luminescence. Here we have a model, and I can move it a little bit and you will be able to see, but we have here some DC power supply. So these supplies provide current which is enough to make our model shine. So let's perform now a simple measurement. Okay, so this is the special camera which allows us to see the luminescence of our device. Probably you can see something, but it's not a good quality image, because still the lights are turned on in this room. But in a minute we will switch it off, and make it, and our image will be, well, better. Anyway, you can see that there are some parts which are darker and some which are brighter than others, and the question is why? The reason is obvious, because when the current flows, it's well, where current can flow, it's easy easily the model shines. Where the current flow is obstructed, you can see these dark areas. Some of these areas indicate that there is some kind of problem in this well, part of the model, but some of them are simply the structure of the cells. Because this is a polycrystalline photovoltaic model, you can see grains of silicon. Okay, so you will be also able to see the most common defect which occurs in photovoltaic models, namely microcracks. So let me show you. Okay, guys, so now we can see in more details some cells of this model. Now you can easily see these dark areas, which are grains of silicon. Of course, these grains somehow influence the current flow, and that's why we can see it. But it's not a, well, it's not a problem, because it's a natural feature of polycrystalline silicon. Nevertheless, also we can somewhere find a microcrack. Let me take a look from the, oh yeah, here we have a cell with microcrack. As you can see, there is a line which somehow splits the cell into two parts. One is a little bit darker than other one, and this is what well, microcracks do. They simply obstruct the current flow, and that's why the cell can't work with its full power. What's worse, all cells in a photovoltaic model are connected in series. That's why the whole model works as the weakest cell, and probably in this case, this is the weakest cell. Other thing which we can observe is that sometimes the frames, the borders of cells, are a little bit darker than the rest of the area. It's a common situation, because usually the borders of cell are less passivated than the rest of it, and that's why the recombination rate at the edge of the cell is higher, and as a result they are darker than the rest of it. So now let's perform a little experiment. Okay, guys, so now, as you can see, this cell is free of defects. Now my friend will hit the cell with a hammer, and we will see if some microcracks will occur or not. As you can see, nothing serious has happened. So let's hit one more time. Again, nothing occurs. And again, nothing occurs. Okay, so as you can see, our model hasn't survived hits with hammer, but well, there is a sacrifice in the name of science. So the second technique which I would like to show you is the thermography. Thermography is well, also a very common technique, which is based again on infrared, as it was in the case of electroluminescence. The difference is that when well, the external power supply isn't required like in the case of electroluminescence test. But because we are inside the room and I want you to show you the temperature field, the PV model is still connected to the DC suppliers. When you want to perform the thermography measurement outside, the conditions should be stable, and also it's really hard to avoid reflections, and there are many factors which influence your imaging. So it's really important to take into account every factor which can influence your measurement. That's why, according to me, the electroluminescence is more precise than thermography. But in this particular case, the image which we will get should be very similar to the image taken by electroluminescence camera. So let me show you how the model looks like in infrared. So as you can see, there is some areas when the temperature is higher, some areas when the temperature is lower. Obviously, when somewhere current cannot flow, it doesn't heat up this part. So that's why it's colder than the parts where it flows. Simultaneously, some parts are hotter because the current through every cell is similar. That's why if a part of cell is damaged and the current doesn't flow through it, the greater current flow through the rest of the cell which works, and as a result its temperature rises. So that's why some parts are colder and some parts are hotter. Thanks to thermography, you can detect microcracks, but it's more sensitive for serious microcracks. Probably if you would have let's say maybe not smaller but microcracks, but I mean microcracks which doesn't strongly influence the current flow, we hadn't seen them. The thermography is also a good technique for PV module diagnostic. It's for sure faster than electroluminescence, but it has some some disadvantages, of course, as electroluminescence. So it's good to have depending on the situation, it's good to utilize both techniques or one of them because of some reasons. So I think I somehow I have presented to you the basic measurements in the field of photovoltaics. So thank you for your attention and maybe see you.